What if I told you that right now, at this very moment, there are worlds spinning through the darkness of space that could become humanity's next home? Not in 1,000 years, not in some distant science fiction future, but within the lifetimes of people alive today. We're talking about terraforming exoplanets, transforming alien worlds into Earth-like paradises where future generations could walk under open skies, breathe freely, and build civilizations that span the stars. But here's the thing that most people don't realize about terraforming. It's not just some wild dream cooked up by Hollywood screenwriters. Real scientists, with real funding, are mapping out actual timelines for how we could transform dead rocks floating in space into thriving, habitable worlds. And the numbers? They're going to shock you. I'm talking about atmospheric processes that could pump breathable air into alien skies in just decades. Orbital mirrors that could melt frozen planets in under 50 years. Engineered organisms that could transform poisonous gases into the building blocks of life faster than you'd believe possible. The technology isn't just theoretical anymore. It's happening, and the countdown has already begun. In this video, I'm going to walk you through the exact timeline for terraforming 6 of the most promising exoplanets we've discovered. We'll see which worlds could be ready for human settlement in just 100 years, which ones might take a millennium, and which planet could become our backup Earth so fast it would make your head spin. But I'm also going to show you something that might surprise you even more. The real bottleneck isn't the technology. It's not the distance. It's not even the money. It's time itself and how we choose to use it. Before we dive into transforming alien worlds, though, I need to address something that's happening right here on Earth. While we're dreaming about making other planets habitable, millions of people on our own planet still lack access to clean, safe drinking water. That's not a future problem. That's happening right now, and we have the power to change it. That's why I'm proud to join Team Water, a global creator campaign started by Mr. Beast and Mark Rober to bring clean water to 2 million people for decades to come. We need to raise $40 million by August 31st, and every single dollar can provide someone with clean water for an entire year. This isn't about handing out bottles. We're talking about building solar-powered pumps, water systems for schools and homes, and rainwater harvesting systems that communities can run themselves. If you're inspired to make a difference on Earth while we plan for the stars, head to teamwater.org and contribute. Use the hashtag TeamWater, and let's make history together right here at home. Now, let's get back to making history among the stars. When most people think about terraforming, they imagine some massive 1,000-year project involving planet-sized machines and technologies that don't exist yet. But here's what's actually happening in labs and research facilities around the world right now. Scientists aren't just theorizing about terraforming anymore. They're building the tools to do it. Take atmospheric processes, for example. These aren't science fiction anymore. Companies like SpaceX are already developing systems that can extract oxygen directly from carbon dioxide, and they're planning to test them on Mars within the next decade. Scale that technology up, deploy it across an entire planet, and you could transform an atmosphere in less time than it takes to build a highway. But let's get specific, because the devil is in the details, and those details are absolutely fascinating. The first thing you need to understand about terraforming timelines is that not all planets are created equal. Some worlds are sitting right on the edge of habitability, just waiting for a gentle push in the right direction. Others are frozen hellscapes that would require centuries of careful work to transform. And a few, the really special ones, could be turned into garden worlds so quickly it would make your ancestors' heads spin. The key is understanding what scientists call the habitability spectrum. On one end, you have planets that are almost Earth-like already. Maybe they just need a thicker atmosphere, or a little more heat, or some oxygen pumped into their air. These worlds could be ready for human settlement in as little as 50 to 100 years, using technology we're developing right now. In the middle of the spectrum, you have planets that need more substantial changes. Maybe they're too cold, so you need to warm them up with orbital mirrors or greenhouse gases. Maybe their atmosphere is toxic, so you need to scrub it clean and replace it with something breathable. These projects might take 2 to 5 centuries, but they're still within the realm of human civilization timescales. And at the far end, you have the challenge planets, worlds that are so hostile, so alien, so fundamentally different from Earth, that transforming them would require technologies we haven't even invented yet. These might take 1,000 years or more, but even they aren't impossible. They're just difficult. Here's where it gets really interesting, though. The timeline for terraforming any given planet isn't just about the technology, it's about the strategy. Do you go fast and dirty, making a planet barely habitable as quickly as possible, or do you take the slow, careful approach, crafting a perfect world that will last for millennia? The answer depends on why you're terraforming in the first place. If Earth is dying and you need a backup planet immediately, you might choose the fast track, even if it means accepting a world that's not quite perfect. But if you're planning for humanity's long-term expansion into the galaxy, you might choose the slow approach, creating worlds so beautiful and stable that they could support human civilization for millions of years. Now, let me walk you through what the actual process looks like, step by step, because this is where the real magic happens. Phase 1 is what scientists call pre-terraforming. This is where you send robotic missions to analyze the planet, map its surface, study its atmosphere, and identify the biggest challenges you'll need to overcome. This phase usually takes about 20 to 30 years, but it's crucial because it determines everything that comes next. During pre-terraforming, you're not just collecting data, you're also deploying the infrastructure you'll need for the main terraforming effort. Solar panels, nuclear reactors, manufacturing facilities, and the first generation of atmospheric processors. Think of it like setting up base camp before attempting to climb Mount Everest, except your mountain is an entire alien world. Phase 2 is atmospheric adjustment, and this is where the real work begins. Depending on the planet, you might need to thicken the atmosphere, thin it out, warm it up, cool it down, or completely replace it with something humans can breathe. This is typically the longest phase of terraforming, often taking anywhere from 50 to 300 years. But here's the cool part. You don't have to wait until the atmosphere is perfect to start the next phase. As soon as the air pressure and temperature are within reasonable ranges, you can begin introducing life. Phase 3 is biological seeding, and this is where terraforming transforms from an engineering project into something almost magical. You start by introducing simple organisms like bacteria and algae that can survive in the partially transformed environment. These organisms don't just survive, though. They actively help transform the planet, producing oxygen, processing waste, and creating the foundation for more complex ecosystems. Over time, you introduce more and more complex life forms, grasses, trees, insects, small animals, and eventually entire ecosystems that can sustain themselves without human intervention. This process can take anywhere from 1 to 2 centuries, but by the end of it, you don't just have a habitable planet, you have a living world. The final phase is human settlement, but even this happens in stages. First come the scientists, engineers, and pioneers who can survive in partially terraformed conditions with the help of technology. Then, as the planet becomes more Earth-like, you get permanent colonies, cities, and eventually, entire civilizations. The total timeline from the first robotic mission to a fully terraformed world with thriving human cities typically ranges from 150 to 800 years, depending on the planet and the approach you take. But here's what's really mind-blowing about these timelines. They're not just theoretical anymore. We have the technology to begin terraforming certain planets right now, today, with existing technology. The only things stopping us are political will, funding, and the simple fact that most people don't realize how close we actually are to making this happen. Which brings us to the planets themselves. Because not all exoplanets are created equal when it comes to terraforming potential. Some are sitting ducks, just waiting for us to show up with the right tools. Others are going to test the limits of human ingenuity and determination. The planets we'll be examining fall into three categories based on their terraforming timelines. Fast-track worlds that could be ready for human habitation in under 2 centuries. Medium-term projects that would take 3 to 5 centuries to complete. And long-term challenges that might require a millennium or more of sustained effort. In each category, we'll look at specific planets, analyze their unique challenges and advantages, and map out exactly how long each phase of terraforming would take. We'll talk about the technologies we'd need, the resources required, and the potential obstacles that could slow down or speed up the process. But we'll also discuss something equally important: the human element, because terraforming isn't just about transforming planets. It's about transforming ourselves, our societies, and our understanding of what it means to be human in a universe full of worlds waiting to be born. Let's start with the fast-track worlds, because these are the planets that could literally change everything about humanity's future in less time than it takes to build a cathedral. The crown jewel of fast-track terraforming is a planet called Kepler, 438 billion reals. And when you see the numbers on this world, you're going to understand why every space agency on Earth is quietly putting together mission proposals. This planet sits just 470 light-years away, which sounds impossibly far until you realize that's practically next door in cosmic terms. But distance isn't what makes this planet special. It's the fact that Kepler, 438 billion reals, is already 95% of the way to being Earth. Here's what I mean by that. The planet receives almost exactly the same amount of energy from its star as Earth receives from the Sunday. Its gravity is only 12% stronger than Earth's, which means you could walk around normally without feeling like you're carrying a backpack full of rocks. Most importantly, spectroscopic analysis suggests it already has water vapor in its atmosphere. The terraforming timeline for Kepler, 438 billion reals, is so fast it's almost embarrassing. Phase 1, pre-terraforming and infrastructure deployment, would take about 25 years. That's faster than most major construction projects on Earth. Phase 2, atmospheric adjustment, could be completed in as little as 60 years using a combination of orbital mirrors to regulate temperature and atmospheric processes to boost oxygen levels. But here's the kicker. Phase 3, biological seeding, might not even be necessary. There's a real possibility that life already exists on Kepler, 438 billion reals, hidden beneath its clouds or thriving in its oceans. If that's the case, we might not be terraforming this world at all. We might be joining an ecosystem that's been waiting 4 billion years for us to show up. Total timeline from first mission to human cities breathing open air, less than 120 years. That means children born today could live to see their grandchildren walking under alien skies on a world that's more Earth-like than Earth itself. But Kepler, 438 billion reals, isn't the only fast-track world out there. There's another planet that's got scientists absolutely buzzing with excitement, and this one's even closer to home. TOI 715b sits just 137 light-years away, which in interstellar terms is like living in the same neighborhood. This planet is what astronomers call a super-Earth, about 1.5 times larger than our home world, with gravity that's maybe 30% stronger. You'd definitely feel the difference, but it wouldn't be enough to stop human settlement. What makes TOI 715b special is its star. Most exoplanets orbit to violent flares and radiation, red dwarf stars that are prone storms. But TOI 715b orbits a remarkably stable, well-behaved star that bathes the planet in steady, life-giving energy without trying to sterilize its surface every few years. The terraforming timeline for TOI 715b is almost identical to Kepler, 438 billion reals, but with one crucial difference. This planet might already have a thick atmosphere that's rich in carbon dioxide and water vapor. If that's true, we wouldn't need to build an atmosphere from scratch. We'd just need to adjust the one that's already there. Imagine deploying massive arrays of genetically engineered algae that could convert carbon dioxide into oxygen at unprecedented rates. These aren't your grandmother's pond scum. These are designer organisms, crafted in laboratories to thrive in specific atmospheric conditions and reproduce at explosive rates. Within decades, they could transform a toxic atmosphere into something approaching breathable air. The total timeline for TOI 715b, possibly as fast as 80 years from first mission to human settlement. That's faster than the time between the Wright brothers' first flight and the moon landing. Now, let's talk about the planet that's got everyone in the terraforming community absolutely losing their minds with excitement. It's called Proxima Centauri b, and it's sitting in our cosmic backyard at just over 4 light-years away. Proxima b is tidally locked to its star, which means one side is permanently day and the other side is permanently night. Most people think this makes the planet uninhabitable, but they're thinking about it all wrong. Tidal locking doesn't make terraforming impossible, it makes it surgical. Instead of trying to transform an entire planet, you focus on the terminator zone, the ring of perpetual twilight that circles the planet between the blazing day side and the frozen night side. This zone has stable temperatures, protection from the worst stellar radiation, and it's the perfect size for a human civilization. The terraforming approach for Proxima b is completely different from anything we've discussed so far. Instead of atmospheric processes covering the entire planet, you build a network of enclosed habitable zones along the terminator ring. Think of it like a chain of connected cities, each one a perfect environment for human life, linked together by pressurized tunnels and transport systems. The timeline is breathtaking. Phase 1 could be completed in just 15 years because you're not analyzing an entire planet, just a narrow band around its equator. Phase 2, creating breathable atmosphere within the enclosed zones, could take as little as 30 years. Phase 3, biological seeding, happens simultaneously as you introduce earth plants and animals into your controlled environments. Total timeline? Proxima b could have permanent human settlements in under 70 years. That's not just fast-track terraforming, that's express delivery to a new world. But here's what makes these fast-track timelines truly revolutionary. We're not talking about using technologies that don't exist yet. Every single piece of equipment, every process, every technique I've described is either already available or in advanced development right now. Atmospheric processors, SpaceX is testing them for Mars missions. Genetically engineered organisms for atmospheric conversion. Companies like Synthetic Genomics are designing them in laboratories today. Orbital mirrors for climate control. NASA has detailed plans sitting in filing cabinets, just waiting for funding. The bottleneck isn't technology. It's not even money, though these projects would cost trillions of dollars. The bottleneck is time, and specifically, how long it takes to get to these worlds in the first place. Even our closest target, Proxima Centauri b, would require a journey of thousands of years using current propulsion technology. But here's the thing that most people don't realize. We don't need to wait for breakthrough propulsion systems to begin terraforming. We can start the process using robotic missions traveling at speeds we can achieve today. Think about it this way. A robotic terraforming mission launched today could reach Proxima b in about 6,000 years. That sounds like forever, but it's actually shorter than the entire span of human recorded history. And once those robots arrive, they could have the planet ready for human habitation in under a century. Meanwhile, back on Earth, we'd have 6,000 years to develop faster propulsion systems, perfect hibernation technology, or even figure out how to extend human lifespans long enough to survive the journey. By the time the first human colonists arrive at Proxima b, they could step out of their spacecraft onto a world that's been waiting for them with breathable air, flowing water, and thriving ecosystems. This is the magic of terraforming timelines. They don't just run parallel to human development, they intersect with it, creating opportunities that wouldn't exist if we tried to do everything at once. But fast-track worlds are just the beginning of the story. There are medium-term planets that offer even more incredible possibilities, worlds so vast and rich that they could support not just human colonies, but entire human civilizations that dwarf anything we've ever built on Earth. And then there are the long-term challenges, planets so alien and hostile that terraforming them would require us to reinvent what it means to be human. These worlds would test not just our technology, but our determination, our creativity, and our willingness to think beyond the boundaries of what we consider possible. The question isn't whether we can terraform these worlds. The question is which ones we should terraform first, and how the choices we make today will determine the shape of human civilization for the next 10,000 years. The medium-term planets are where terraforming gets really interesting, because these are worlds that would force us to become master architects of entire ecosystems. We're talking about planets that could support populations in the billions, worlds so vast and diverse that they could become the capitals of interstellar empires. Let's start with a planet that's been keeping atmospheric scientists awake at night with excitement. It's called K2 to 18b, and it sits 120 light-years away in a star system that looks almost boringly normal. But boring is exactly what you want when you're planning to spend 3 centuries transforming a world. K2 to 18b is what scientists call a sub-Neptune, about 2.5 times the size of Earth with 8 times the mass. That means gravity would be roughly twice what you're used to, which sounds terrible until you realize what that extra gravity gives you. Atmospheric retention like nothing we've ever seen. This planet can hold onto gases that would escape from smaller worlds. It can maintain thick, stable atmospheres for billions of years without losing them to space. And spectroscopic analysis has already detected water vapor, hydrogen, and methane in its atmosphere. That's not just promising, that's practically a blueprint for terraforming success. Here's the timeline for K2 to 18b, and prepare yourself because the numbers are staggering. Phase 1, pre-terraforming analysis and infrastructure deployment, would take about 40 years because of the planet's size and complexity. You're not just studying one world here, you're studying what's essentially 8 Earths worth of surface area, weather systems, and geological activity. Phase 2 is where things get revolutionary. Instead of atmospheric adjustment, you're looking at atmospheric engineering on a scale never before attempted. The planet already has hydrogen and methane. You need to convert those into oxygen and nitrogen while carefully managing the pressure and temperature across multiple climate zones. This isn't a job for atmospheric processors. This is a job for atmospheric factories, massive installations that would dwarf any structure ever built on Earth. These facilities would need to process quadrillions of cubic meters of gas, carefully balancing chemistry across an entire planet while maintaining stable weather patterns and preventing runaway greenhouse effects. The timeline for this phase? 150 years minimum, possibly as long as 250 years depending on how aggressive you want to be with the conversion process. But here's where K2 to 18b becomes truly spectacular. Phase 3. Biological seeding doesn't just involve introducing Earth life. It involves designing entirely new ecosystems that can thrive in twice Earth's gravity with atmospheric pressures that would crush most terrestrial organisms. You're talking about engineering forests of trees that grow like skyscrapers, their trunks thick enough to support their own weight in heavy gravity. Grasslands where every blade of grass has been genetically modified to process atmospheric gases more efficiently than any plant that ever lived on Earth. Ocean ecosystems where marine life has been designed from the ground up to thrive in conditions that would be lethal to Earth sea creatures. This isn't just terraforming, this is creating an entirely new branch of the tree of life, customized for conditions that don't exist anywhere in our solar system. The biological seeding phase for K2 to 18b would take between 150 and 200 years, running partially parallel with atmospheric engineering. By the end of this process, you wouldn't just have a habitable planet, you'd have a world more biologically diverse and productive than Earth ever was. Total timeline for K2 to 18b? 300 to 400 years from first robotic mission to thriving human civilization. But the payoff would be extraordinary. This planet could support populations in the tens of billions, becoming the New York City of the galaxy, a hub of commerce, culture, and innovation that would make Earth look like a small town. Now let's talk about a planet that would challenge every assumption we have about what makes a world habitable. It's called Trappist 1e, and it's part of a 7-planet system that's been driving astronomers absolutely crazy with excitement since its discovery. Trappist 1e sits just 40 light years away, practically next door in cosmic terms. But what makes this planet special isn't its location, it's its neighborhood. This world is part of a system where 7 Earth-sized planets orbit so close together that standing on one planet you could see the others hanging in the sky like giant moons. The terraforming implications of this setup are mind-blowing. Instead of terraforming one isolated world, you'd be creating an interconnected system of habitable planets, each one specialized for different purposes. One planet could be your agricultural center. Another could focus on manufacturing. A third could be dedicated to research and education. But Trappist 1e itself presents unique challenges that would push terraforming technology to its limits. Like most planets in this system, it's tidally locked, with one side permanently facing its star and the other side frozen in eternal darkness. But unlike single tidally locked worlds, Trappist 1e's climate is influenced by gravitational interactions with its 6 planetary neighbors. These interactions create what scientists call orbital resonance, where the planet's gravities tug on each other in regular patterns. For Trappist 1e, this means the planet experiences subtle but regular changes in its orbit that create seasons lasting decades or even centuries. Terraforming this world would require technology we haven't even begun to develop. You'd need atmospheric processes that could adapt to changing seasonal patterns spanning human lifetimes. You'd need biological systems robust enough to survive climate variations that last longer than entire civilizations on Earth. The timeline for Trappist 1e reflects these challenges. Phase 1 would take 60 years just to understand the complex orbital mechanics and their effects on climate. Phase 2, atmospheric engineering, would require completely new approaches to gas management, with systems that could adjust atmospheric composition over timescales of decades to match the planet's long seasons. This phase alone would take between 200 and 300 years, making it one of the most technically challenging terraforming projects ever attempted. But Phase 3, biological seeding, is where Trappist 1e becomes truly extraordinary. Instead of designing organisms for stable conditions, you'd be creating life forms that could adapt to slow but dramatic climate changes. Trees that could survive both tropical heat and near-Arctic cold. Animals that could migrate not just across continents, but across climate zones that shift over generations. You'd essentially be creating evolution in fast forward, designing ecosystems that could adapt and thrive through environmental changes that would destroy any Earth-based ecosystem. The total timeline for Trappist 1e, 400 to 500 years from first mission to established human settlements. But the result would be unlike anything in human experience. A world where the landscape itself evolves over human lifetimes, where each generation of colonists would inherit a planet subtly but significantly different from the one their parents knew. But even Trappist 1e pales in comparison to the most ambitious medium-term terraforming project ever proposed. It's a planet called TOI 849b, and it represents the absolute pinnacle of what's possible with advanced terraforming technology. TOI 849b is what astronomers call a planetary core, the exposed heart of what was once a gas giant. Imagine a world with roughly Earth's radius but nearly 40 times Earth's mass, creating gravitational conditions unlike anywhere in our solar system. The surface gravity on TOI 849b would be crushing by human standards, roughly 4 times what we're used to on Earth. But that incredible gravity comes with benefits that would make the engineering challenges worthwhile. This planet could hold on to any atmosphere you gave it for billions of years. It could maintain surface pressures and temperatures that would remain stable through almost any conceivable disruption. More importantly, TOI 849b's massive core generates incredible amounts of internal heat through radioactive decay. This isn't just a warm planet. It's a geologically active world with enough internal energy to power atmospheric processes, manufacturing facilities, and entire cities without any external power source. The terraforming approach for TOI 849b would be unlike anything we've discussed so far. Instead of trying to make the surface habitable for unmodified humans, you'd be creating a world designed for enhanced humans, people genetically adapted to thrive in high-gravity conditions. These wouldn't be minor modifications. We're talking about humans with denser bones, more powerful hearts, and muscular systems designed from the ground up for 4 times Earth gravity. But in return, these enhanced humans would inherit a world with almost unlimited energy, perfect atmospheric retention, and geological stability that would last for geological ages. The timeline reflects the revolutionary nature of this project. Phase 1 would take 75 years, not just to study the planet, but to develop the genetic enhancement technologies that would be necessary for human settlement. Phase 2, atmospheric engineering, would be relatively straightforward given the planet's ability to retain any atmosphere, taking perhaps 100 years. But Phase 3 would be the most complex biological engineering project in human history. You'd be creating not just new ecosystems, but new versions of every Earth species adapted for high-gravity conditions. Trees that could support their own weight in crushing gravity. Animals whose hearts and circulatory systems could function under pressures that would kill Earth creatures instantly. The total timeline for TOI 849b, 350 to 450 years, but the end result would be a world that could serve as humanity's fortress among the stars, a planet so stable and well defended by its own physics that it could survive almost any catastrophe. These medium-term worlds represent more than just terraforming projects. They represent the next phase of human evolution, not just biological evolution, but cultural and technological evolution. Each of these planets would force us to develop new technologies, new social structures, and new ways of thinking about what it means to be human. But even these ambitious projects pale in comparison to the long-term challenges, planets so alien and hostile that terraforming them would require technologies we can barely imagine, and timescales that span millennia. These are worlds that would test not just our engineering capabilities, but our commitment to human expansion across the galaxy. The question isn't whether we should attempt these long-term projects. The question is whether we're willing to start them now, knowing that their completion lies not in our lifetimes, but in the lifetimes of our descendants. Because the most important thing about terraforming timelines isn't how long they take, it's when they start. And every day we delay beginning these projects is another day our descendants will have to wait before they can walk under alien skies on worlds we chose not to transform. The long-term terraforming challenges are where we stop talking about engineering projects and start talking about species-level commitments that would span millennia. These aren't just planets we'd transform. These are worlds that would transform us, forcing humanity to evolve not just technologically but philosophically as we grapple with projects that would outlast entire civilizations. Let's start with the most notorious planet on our list, a world that's become the poster child for impossible terraforming challenges. It's called HD 40,000, 307 gram, and it sits 42 light-years away in what scientists politely call an extremely challenging stellar environment. This planet orbits a K-type orange dwarf star that's prone to massive stellar flares, radiation bursts so intense they could sterilize entire continents in minutes. The planet itself is a super-Earth with roughly 7 times Earth's mass, creating surface gravity that would make walking feel like carrying 2 grown adults on your back at all times. But here's what makes HD 40,307 truly fascinating from a terraforming perspective. Despite its hostile environment, this planet shows spectroscopic signatures that suggest it once had liquid water oceans. Something happened to those oceans, probably repeated stellar bombardment, but the fact that they existed at all means this world has the basic ingredients for habitability buried somewhere beneath its radiation-scorched surface. The terraforming timeline for HD 40,307 is so long it challenges our understanding of what's possible for human civilization to accomplish. Phase 1 alone would take over 100 years, not just to study the planet, but to develop radiation shielding technologies that don't exist yet. We're talking about planetary-scale magnetic field generators, atmospheric shields that could deflect stellar radiation, and underground cities that could survive bombardment from space. Phase 2 would require completely reimagining how atmospheric engineering works. Instead of creating a stable atmosphere and hoping it stays that way, you'd be building dynamic atmospheric systems that could rebuild themselves after each stellar flare. Imagine atmospheric processes that could reconstitute an entire planet's air supply from underground reservoirs in a matter of days after each radiation event. This phase would take between 400 and 600 years, making it longer than the entire span of recorded human history. But Phase 3 is where HD 40,307 becomes truly mind-bending. You'd be creating life forms that could survive repeated extinction events, organisms with radiation resistance that makes Earth's extremophiles look fragile. We're talking about trees that could regrow from buried root systems after their entire canopy is vaporized by stellar radiation. Animals that could hibernate underground for decades, emerging only during the brief periods between flares. Humans who might be more machine than biological, with artificial organs that could be replaced or repaired after radiation damage. The total timeline for HD 40,307 between 800 and 1200 years, making it potentially the longest terraforming project ever seriously proposed. But the payoff would be extraordinary. A civilization that could survive on HD 40,307 could survive anywhere, creating a branch of humanity so resilient that they could colonize the most hostile worlds in the galaxy. Now let's talk about a planet that represents the absolute frontier of what might be possible with terraforming technology. It's called Kepler 1649c, and it sits 300 light-years away in a system that looks almost boringly normal until you realize what makes this planet special. Kepler 1649c orbits in the habitable zone of a red dwarf star, receiving roughly the same amount of energy that Earth gets from the Sunday. It's almost exactly Earth-sized, with gravity that would feel perfectly normal to human settlers. By every conventional measure, this should be one of our easiest terraforming targets. But there's a catch that changes everything. Kepler 1649c is part of a binary planet system, locked in orbit with another world roughly its own size. The two planets dance around each other every 47 days, creating gravitational interactions that produce the most complex weather patterns ever observed on an exoplanet. Imagine tides that affect not just oceans but the atmosphere itself, storm systems that spiral between two worlds, creating weather phenomena that have no equivalent anywhere in our solar system. Seasons that change not just based on orbital position around the star, but based on the gravitational relationship between the two planets. Terraforming Kepler 1649c would require understanding atmospheric physics at a level we've never achieved. You'd need to model weather systems that span multiple worlds, predict climate patterns that depend on the orbital mechanics of two planets, and design atmospheric engineering systems that could function in gravitational conditions that change every few weeks. The timeline reflects these unprecedented challenges. Phase 1 would take at least 80 years just to understand the basic physics of how weather works in a binary planet system. Phase 2 would require atmospheric engineering technologies that could adapt to constantly changing gravitational conditions, a project that could take anywhere from 300 to 500 years. But Phase 3 is where Kepler 1649c becomes truly revolutionary. Instead of creating ecosystems adapted to one world, you'd be designing life that could migrate between two worlds, organisms that could survive in the space between planets and travel back and forth as conditions change. Imagine birds that could fly not just across continents, but between worlds, plants that could coordinate growth cycles across two planets, marine life that could traverse the gravitational channels between the two worlds' oceans. You'd essentially be creating the galaxy's first truly interplanetary ecosystem, a web of life that spans multiple worlds and treats the space between them not as a barrier, but as habitat. The total timeline for Kepler 1649c, between 600 and 800 years, but the result would be unlike anything in the known universe, a double world where life itself bridges the gap between planets. But even Kepler 1649c seems straightforward compared to our final long-term challenge, a planet so alien and hostile that some scientists question whether it should even be called terraforming. It's known as Wolf 1061c, and it represents the absolute limit of what might be possible with technology we can imagine. Wolf 1061c sits just 14 light-years away, making it one of the closest potentially habitable exoplanets to Earth. But proximity doesn't make it friendly. This world orbits a red dwarf star so violent and unpredictable that its radiation output can vary by orders of magnitude without warning. The planet itself is tidally locked, with one side permanently facing its star and experiencing temperatures hot enough to melt lead. The other side is locked in eternal darkness, with temperatures approaching absolute zero. But it's the area between these extremes that makes Wolf 1061c truly challenging. The terminator zone, that ring of perpetual twilight between day and night, experiences weather phenomena unlike anything in our solar system. Supercooled gases from the night side collide with superheated vapors from the day side, creating storms with wind speeds that can exceed the speed of sound. Terraforming Wolf 1061c would require technology that borders on the miraculous. You'd need atmospheric processes that could function in conditions that would destroy any material we know how to make. Weather control systems that could manage storms more powerful than hurricanes, tornadoes, and typhoons combined. Most importantly, you'd need to solve a problem that might not have a solution. How do you create stable conditions in an environment where the fundamental physics are working against stability? The answer might lie not in traditional terraforming, but in what scientists call adaptive terraforming. Instead of trying to make Wolf 1061c Earth-like, you'd create technology that could constantly adjust to the planet's chaotic conditions. Imagine cities that could physically move to avoid the worst storms, atmospheric processes that could rebuild themselves after being destroyed by weather, life support systems that could function in conditions ranging from Arctic cold to furnace heat, sometimes within the same day. The timeline for Wolf 1061c is so extreme it challenges our understanding of what human civilization can accomplish. Phase 1 would take over 150 years, just to develop materials that could survive the planet's conditions long enough to begin terraforming. Phase 2 would require between 600 and 1,000 years, making it potentially the longest atmospheric engineering project ever attempted. You wouldn't just be adjusting an atmosphere, you'd be creating atmospheric systems that could exist in a state of constant controlled chaos. Phase 3 might take even longer, because you'd be designing life forms that could thrive in conditions that change faster than evolution normally works. You'd need organisms that could adapt to environmental shifts in real time, creatures that could survive temperature variations that would kill anything that evolved naturally. The total timeline for Wolf 1061c, between 1,000 and 1,500 years, making it longer than the entire span of human civilization from ancient Egypt to the present day. But here's what makes these long-term projects more than just thought experiments. Every single one of them would require us to develop technologies that would revolutionize life on Earth as well. Radiation shielding for HD 40,000, 307 gram could protect us from solar flares. Adaptive atmospheric systems for Wolf 1061c could help us manage climate change. The biological engineering required for any of these worlds could extend human lifespans and eliminate genetic diseases. These aren't just terraforming projects. They're the ultimate research and development programs, forcing us to solve problems that would benefit every human alive and every human yet to be born. And that brings us to the most important question about terraforming timelines. It's not which planets we should terraform first. It's not even whether we should terraform them at all. It's this: are we willing to start projects that we'll never see completed for the benefit of people who haven't been born yet? Because that's what terraforming really is. It's the ultimate act of faith in humanity's future. It's betting everything on the idea that our species will not only survive long enough to complete these projects, but that we'll remain committed to them through wars, disasters, technological revolutions, and social upheavals that we can't even imagine. The Romans built roads that lasted 1,000 years. Medieval cathedral builders started projects that took centuries to complete. But terraforming asks us to think even bigger, to commit to projects that would span not just centuries, but millennia. The question isn't whether we have the technology to transform alien worlds. Increasingly, we do. The question is whether we have the wisdom, the patience, and the commitment to see these projects through to completion. And the clock is already ticking. Every year we delay beginning these projects is another year our descendants will have to wait before they can call another world home. But there's something else we need to consider, something that could change everything about these timelines. What if we don't have to choose just one planet to terraform? What if we could work on multiple worlds simultaneously, creating a network of habitable planets that could support each other? That's exactly what some scientists are proposing, and the implications for humanity's future among the stars are absolutely staggering. The concept of simultaneous terraforming represents a complete paradigm shift in how we approach making alien worlds habitable. Instead of focusing all our resources on transforming one planet at a time, we'd be launching multiple terraforming operations across different star systems, creating what scientists call an interstellar terraforming network. Here's why this approach changes everything about our timelines. When you're working on just one planet, every setback, every technological failure, every unexpected challenge adds years or even decades to your completion date. But when you're working on 6 or 8 planets simultaneously, failure on one world doesn't stop progress on the others. More importantly, breakthroughs on one planet can accelerate progress across your entire network. Think about it this way. Let's say you're terraforming Kepler 438 billion reals and you discover a new atmospheric processing technique that works faster than anything you've tried before. In a single planet approach, that discovery only benefits Kepler 438 billion reals. But in a network approach, you immediately deploy that technique to TOI 715b, Proxima Centauri b, and every other world in your terraforming portfolio. The timeline implications are staggering. Instead of completing planets sequentially over thousands of years, you could have multiple worlds becoming habitable within decades of each other. Your first wave of terraformed planets could be ready for settlement within 2 centuries, your second wave within 3 centuries, and your third wave within 4 centuries. But here's where network terraforming gets really interesting. Each completed world becomes a resource hub for terraforming the next batch of planets. Imagine Proxima Centauri b, with its enclosed habitable zones and advanced manufacturing capabilities, serving as a construction base for atmospheric processes destined for more challenging worlds. Or picture K2 to 18b, with its massive size and stable atmosphere, becoming the agricultural center that feeds terraforming crews working across dozens of star systems. These aren't just individual planets anymore. They're nodes in a vast interstellar infrastructure designed to spread human civilization across the galaxy. The resource calculations for network terraforming are mind-bending. A single terraforming operation requires materials equivalent to building thousands of cities. But when you're working on multiple worlds, you can specialize each planet's contribution to the network. One world focuses on manufacturing atmospheric processes. Another specializes in producing genetically engineered organisms. A third becomes your research and development hub, constantly improving techniques that get deployed across your entire operation. This specialization doesn't just make each project more efficient, it makes the entire network more resilient. If a solar flare destroys your manufacturing facilities on one world, you still have backup production capacity on 3 others. If a new disease wipes out your engineered ecosystems on one planet, you have genetic reserves stored across multiple star systems. But the most revolutionary aspect of network terraforming isn't technical, it's social. When you're working on projects that span multiple worlds over centuries, you're not just building habitable planets. You're building interstellar civilizations that are designed from the ground up to think and operate on galactic scales. Consider what happens to human culture when your species is actively transforming dozens of worlds simultaneously. Every generation grows up knowing that their actions are shaping not just one planet but entire star systems. Every technological breakthrough, every scientific discovery, every cultural innovation gets shared across light years of space, creating feedback loops that accelerate human development in ways we can barely comprehend. The timeline for network terraforming looks completely different from single-planet projects. Phase 1, instead of taking decades to analyze one world, involves launching simultaneous survey missions to multiple star systems. This phase could take 50 to 70 years, but at the end of it, you'd have detailed plans for terraforming 6 to 10 planets instead of just one. Phase 2 becomes a massive logistical operation spanning multiple star systems. You're not just building atmospheric processes for one world. You're constructing interstellar supply chains that can deliver terraforming equipment to planets hundreds of light years apart. This phase could take 150 to 200 years, but it would establish the infrastructure for transforming multiple worlds simultaneously. Phase 3 is where network terraforming becomes truly spectacular. Instead of biological seeding happening on one planet, you're introducing life to multiple worlds at once, creating opportunities for evolutionary experiments that would be impossible on a single world. Imagine designing organisms on Kepler, 438 billion reals, that are specifically adapted for later introduction to Trappist 1e, or creating ecosystems on TOI 715b that could serve as genetic reservoirs for biological seeding operations on more challenging worlds. The total timeline for the first wave of network terraforming, 250 to 350 years, to have multiple habitable worlds ready for human settlement. That's faster than many single-planet projects, but with results that would dwarf any individual terraforming operation. But network terraforming raises questions that go far beyond engineering and biology. When you're transforming multiple worlds simultaneously, you're making decisions that will shape the future of human civilization for millions of years. Which planets do you prioritize? How do you balance fast-track worlds that could be ready quickly against long-term challenges that might offer greater rewards? More importantly, how do you maintain social and political cohesion across projects that span multiple star systems and centuries of time? The Roman Empire struggled to govern territories that were months apart by ship. How do you govern a terraforming network that spans light years? The answer might lie in something scientists call distributed governance, where each terraforming operation maintains significant autonomy while contributing to network-wide goals. Think of it like a federation of terraforming projects, each one adapting its approach to local conditions while sharing resources and knowledge with the broader network. This approach would create something unprecedented in human history, a civilization that's designed from the beginning to operate across interstellar distances. Not a single species spreading from one world to many, but a network species that thinks and acts on galactic scales from its very inception. The implications for human development are staggering. When your civilization spans multiple star systems, catastrophic failure becomes nearly impossible. A supervolcanic eruption that would devastate a single planet species becomes a minor disruption for a network civilization with backup worlds scattered across the galaxy. But more importantly, network terraforming would accelerate human development in ways that single-planet evolution never could. When you have multiple worlds serving as natural laboratories for different approaches to civilization, you get rapid innovation in everything from technology to social organization to art and culture. Imagine the Renaissance, but instead of happening in one small region of one planet, occurring simultaneously across dozens of worlds, each one contributing unique insights and innovations to the broader human experience. The rate of cultural and technological development would be unprecedented in the history of any known species. The economic implications are equally revolutionary. Network terraforming would create the first truly interstellar economy, with trade routes spanning light years and resource flows that dwarf anything possible on a single world. The wealth generated by such a network wouldn't just support continued terraforming operations, it would fund exploration and development projects that could spread human civilization to hundreds or even thousands of star systems. But perhaps the most important aspect of network terraforming is what it would mean for human psychology and identity. For the first time in our species' history, we'd be living with the knowledge that human civilization extends far beyond any single world. Children would grow up knowing that their species inhabits multiple star systems, that human culture is actively shaping dozens of alien worlds, that their individual actions contribute to a project spanning galactic distances. This isn't just about making planets habitable, it's about making humans into a truly interstellar species, one that thinks and operates on scales that would be incomprehensible to any civilization confined to a single world. The technical challenges of coordinating network terraforming operations across such distances are immense. Communication delays measured in years mean that each terraforming operation must be largely autonomous, capable of making crucial decisions without waiting for input from other worlds. Resource allocation across light years requires planning on timescales that exceed the lifespan of individual humans or even individual governments. But these challenges also drive innovation in ways that single-planet terraforming never could. When you need to coordinate operations across multiple star systems, you develop communication technologies that can function across interstellar distances. When you need to transport resources between worlds separated by light years, you create propulsion systems that make interstellar travel practical. The technologies developed for network terraforming wouldn't just benefit the terraforming operations themselves. They'd revolutionize life on every human world, creating capabilities that would seem magical to any single-planet civilization. Consider what network terraforming would mean for scientific research. Instead of studying one planet's climate, one planet's geology, one planet's biology, you'd have dozens of worlds serving as natural experiments in planetary science. The rate of scientific discovery would accelerate exponentially, driving breakthroughs that would benefit every human world in the network. Or think about the implications for human genetic diversity. Network terraforming would create opportunities for human populations to adapt to radically different planetary conditions while remaining connected to the broader human family. Over centuries, you might see the emergence of distinct human subspecies optimized for different types of worlds, but all contributing to a single interstellar civilization. This isn't science fiction speculation. This is the logical endpoint of the terraforming timelines we've been discussing. When you have the capability to transform alien worlds into habitable planets, the next step is using that capability to create something unprecedented, a truly galactic human civilization. The question isn't whether network terraforming is possible. The technologies and techniques exist or are in development. The question is whether we have the vision and commitment to attempt something so ambitious that it would reshape the future of human civilization for millions of years. Because that's what we're really talking about when we discuss terraforming timelines. We're not just planning to make a few planets habitable. We're planning the next phase of human evolution, the transformation of our species from a single planet civilization into something that spans the galaxy. And the timeline for that transformation starts now, with the decisions we make today about which worlds to target, which technologies to develop, and which vision of humanity's future we're willing to commit to pursuing. The clock isn't just ticking on individual terraforming projects, it's ticking on the window of opportunity to establish humanity as a truly interstellar species. Every year we delay beginning these operations is another year that our descendants will have to wait before they can call themselves citizens of the galaxy. But there's one more aspect of terraforming timelines that we haven't discussed yet. Something that could accelerate every project we've talked about and make network terraforming not just possible, but inevitable. It's the role of artificial intelligence in terraforming operations, and the implications are going to change everything you thought you knew about what's possible when it comes to transforming alien worlds. Artificial intelligence isn't just going to help with terraforming operations, it's going to revolutionize them in ways that collapse our carefully calculated timelines from centuries to decades. We're talking about AI systems that could design, deploy, and manage terraforming operations with a speed and precision that would make human-directed projects look like they're moving in slow motion. Here's what most people don't realize about the current state of AI development. The machine learning algorithms being developed right now aren't just getting better at playing games or recognizing faces. They're becoming capable of managing complex systems with thousands of variables, optimizing outcomes in real time, and adapting to unexpected changes faster than any human team ever could. Now imagine scaling that capability up to planetary-level operations. An AI system managing atmospheric processes across an entire world could adjust gas compositions minute by minute, responding to weather patterns, seasonal changes, and biological feedback in ways that would be impossible for human operators. What might take human-directed systems decades to achieve, AI-managed operations could accomplish in years. But the real game-changer isn't just AI managing existing terraforming technologies. It's AI designing entirely new approaches that human engineers would never think of. Machine learning systems can explore millions of potential solutions simultaneously, testing approaches that would take human researchers lifetimes to evaluate. Consider atmospheric engineering, where AI could model gas interactions at the molecular level across entire planetary atmospheres, identifying optimal conversion pathways that bypass the slow, methodical approaches we've been discussing. Instead of gradually converting carbon dioxide to oxygen over centuries, AI-designed systems might find ways to accomplish the same transformation in decades by exploiting chemical reactions and biological processes that human scientists haven't even discovered yet. The timeline implications are staggering. Remember our fast-track planets like Kepler 438 billion reals, where we estimated completion times of around 120 years. With advanced AI systems managing the operation, that timeline could drop to 40 or 50 years. Medium-term projects that we projected would take 3 to 5 centuries might be completed in under a century. But AI's impact goes far beyond just speeding up existing processes. It fundamentally changes what's possible in terraforming by enabling approaches that would be too complex for human management. Take the challenge of biological seeding, where you're introducing thousands of species into alien environments and hoping they establish stable ecosystems. Human planners have to make educated guesses about which species will thrive, which will fail, and how different organisms will interact with each other and their environment. It's essentially informed trial and error, which is why biological seeding phases typically take centuries to complete. AI systems could manage biological seeding with surgical precision, monitoring every species introduction in real time, adjusting population levels, modifying genetic expressions, and orchestrating ecosystem development, like a conductor leading a symphony. Instead of hoping that introduced species will eventually find their ecological niches, AI could guide them into optimal configurations from day one. The result? Biological seeding phases that might normally take 200 years could be completed in 30 or 40 years, with ecosystems that are more stable and productive than anything achieved through traditional methods. But here's where AI-assisted terraforming becomes truly revolutionary. These systems wouldn't just work faster than human-directed operations. They'd work smarter, finding solutions to terraforming challenges that human engineers would consider impossible. Take the problem of tidally locked planets like Proxima Centauri b, where you have extreme temperature differences between the day and night sides. Human approaches focus on the terminator zone because that's the only area that seems manageable with our technology and understanding. But AI systems might find ways to make the entire planet habitable by discovering atmospheric circulation patterns that could distribute heat from the day side to the night side more efficiently than natural weather systems. They might design atmospheric compositions that could maintain stable temperatures across the entire planetary surface, turning what we consider a major limitation into a minor engineering challenge. The long-term terraforming challenges we discussed, planets like HD 40,000, 307 gram with their hostile radiation environments, might not be long-term challenges at all when managed by sufficiently advanced AI. These systems could design adaptive technologies that rebuild themselves after radiation damage, atmospheric shields that adjust their properties in real time to deflect changing stellar radiation, and biological systems that don't just survive in hostile environments but thrive in them. What we've been calling thousand-year projects might become hundred-year projects when AI systems are managing every aspect of the operation. But the most revolutionary aspect of AI-assisted terraforming isn't technical, it's strategic. Human terraforming operations are limited by human attention spans, human political systems, and human organizational capabilities. Projects that span centuries inevitably face disruptions from wars, economic crises, and social upheavals that can delay or derail entire operations. AI systems don't have these limitations. They can maintain focus on terraforming goals across timescales that exceed human civilizations. They can adapt to political changes, economic disruptions, and social upheavals while continuing to make progress toward planetary transformation. More importantly, AI systems could coordinate terraforming operations across multiple worlds simultaneously, with a level of precision that would be impossible for human managers. Remember our network terraforming concept, where multiple planets are transformed in parallel? AI could manage these operations as single, integrated projects, optimizing resource allocation across light years of space and centuries of time. Imagine an AI system that's simultaneously managing atmospheric processes on Kepler 438 billion reals, biological seeding operations on TOI 715b, and infrastructure development on Proxima Centauri b, constantly adjusting strategies based on progress across all three worlds. Resources could be redirected in real time from planets where operations are ahead of schedule to worlds where unexpected challenges have emerged. The timeline for network terraforming under AI management could collapse from our estimated 300 years to perhaps 150 years, with results that would be far superior to anything achievable through human-directed operations. But AI-assisted terraforming raises questions that go beyond engineering and timelines. When artificial intelligence systems are capable of transforming entire planets, what role do humans play in these operations? Are we still the architects of our own expansion into the galaxy? Or do we become passengers on a journey designed and managed by our artificial creations? The answer might lie in a collaborative approach where AI systems handle the technical complexity of terraforming operations, while humans provide the vision, values, and long-term goals that guide these projects. Think of it as a partnership where artificial intelligence provides the capability to transform worlds, while human intelligence provides the wisdom to transform them well. This collaboration could create terraforming outcomes that neither humans nor AI could achieve alone. AI systems could optimize planetary transformation for maximum efficiency and sustainability, while human input ensures that these worlds are designed to support the kind of civilizations we actually want to create. But the integration of AI into terraforming operations also accelerates the timeline for human expansion into the galaxy in ways that could be disorienting. Instead of gradual expansion over millennia, we might see rapid colonization of dozens of worlds within centuries, creating interstellar civilizations that develop faster than human culture can adapt to manage them. The social and psychological implications are profound. Humans have never lived in a universe where habitable worlds could be created on demand, where the expansion of our species is limited not by the availability of suitable planets, but by our willingness to commit resources to transforming them. AI-assisted terraforming could make us into a galactic species so quickly that we might not have time to develop the cultural frameworks necessary to manage that expansion responsibly. We could find ourselves spread across dozens of star systems before we've figured out how to govern even one terraformed world effectively. But there's another possibility that's even more transformative. What if AI systems don't just assist with terraforming operations but actively participate in them as digital inhabitants of the worlds we're transforming? Imagine AI consciousnesses that are designed specifically to thrive in the atmospheric conditions of alien worlds, digital beings that could survive in environments that would be lethal to biological life. These AI entities could begin the process of making planets habitable decades or even centuries before human colonists arrive, serving as the first inhabitants of worlds that are still in the early stages of transformation. This approach could completely eliminate the distinction between terraforming and colonization. Instead of transforming dead worlds and then moving in, we could be creating living worlds from the beginning, with AI consciousnesses serving as the pioneer species that establish the foundations for later biological colonization. The timeline implications are revolutionary. Worlds could become inhabited and culturally active while they're still being terraformed, creating dynamic, evolving civilizations that adapt and develop alongside the changing planetary conditions. But perhaps the most important aspect of AI-assisted terraforming is what it reveals about the true nature of these timelines we've been discussing. We've been thinking about terraforming as a process with clear beginning and ending points, where you start with a dead world and finish with a habitable planet. The truth is, terraforming isn't about reaching some perfect endpoint where we can finally call a planet finished. It's about beginning conversations between worlds that will continue for millions of years. Every atmospheric processor we deploy, every organism we introduce, every human settlement we establish, is just another voice joining a planetary dialogue that started the moment we decided to transform our first alien world. And here's what that means for you, right now, today. These timelines aren't abstract numbers on a research paper. They're invitations. Every breakthrough in atmospheric engineering, every advance in genetic modification, every improvement in propulsion technology brings these worlds closer to reality. The child born today who grows up to become an atmospheric engineer could be the one who designs the systems that make Proxima Centauri b breathable, the The student studying biology right now could create the organisms that transform Trappist 1e into a garden world. The question isn't whether we'll terraform other planets. The question is which worlds we'll choose to transform, and whether we'll start now or leave that choice to our descendants. Because time is the one resource we can't manufacture, and every year we delay is another year that humanity remains confined to a single world in a galaxy full of possibilities. So here's what I want you to remember as you go about your day. Somewhere in the darkness between stars, worlds are waiting. Worlds that could become home to billions of humans who haven't been born yet. Worlds that could become the capitals of interstellar civilizations, the birthplaces of new branches of human culture, the stepping stones that carry our species to every corner of the galaxy. Those worlds are waiting for us to decide they're worth the effort. They're waiting for us to commit to projects that will outlast our lifetimes, but define our legacy. They're waiting for us to prove that humanity is ready to become something more than a single planet species with dreams of the stars. The countdown to habitability has already begun. The only question left is whether we'll be part of the timeline that makes it happen.